Hi, my name is Kevin Farlee. I'm a program manager in the SQL Server team at Microsoft. I've been on the SQL team for about 15 years. Worked on a lot of different features over the years. Right now my focus is on HA, but one of the interesting things is that I've spent a lot of time in the InMemory Database area. So that's what we're going to talk about this morning. So this talk is about turbocharging your SQL Server with InMemory Database. The whole idea here is that by leveraging in-memory technologies, it's going to make your SQL Server move much faster in a number of different ways. And there's different strategies we can use for different types of workloads that'll make it faster. We'll get into all that. So what is an in-memory database? In one way of thinking, your database has always been in memory, right? Because anytime you interact with that data, it has to be in memory before we can interact with it. We use memory to make the data access faster, so we'll pull the data into the buffer pool, which is just a structured area for keeping data in memory. So when you issue a query for data, if the data isn't already in the buffer pool, the request goes down to the disk. Disk is retrieved, pulls the data into the buffer pool, and then returns the data to you. And the unit of data here is a page. So a data page is just a set unit of data in a very structured organization. It makes for a handy package of data to move back and forth between disk and memory. So it's a very consistent way of packaging data to move it in and out. It doesn't really interact with the data itself. It's just a way of packaging that memory for movement back and forth between memory and disk. If that page is already in memory when you issue the read, it's what we call a logical read, which means we just read it right out of the buffer pool. We don't ever go down to the disk. So you want to keep that data in buffer pool as much as possible. That way you're not making the trip out to the physical disk device. Same's true for writes. We never modify pages directly on disk. We always bring it into the buffer pool first. So you're going to pull it into the buffer pool, even if you're not doing an explicit query. You say update this data where this predicate. The predicate is going to bring that page into memory first. Even if you're only modifying a single row, and that may be a very small row, the only unit we can move between disk and memory, disk and buffer pool, is a page. So we're going to bring that whole page into memory. And then if we're updating it, we have to latch it in memory to keep two threads from conflicting on the same page. There's a lot of physical structures and pointers and counters within that data page, and they must all be kept consistent. If two threads were trying to update, say inserting different rows within that same page at the same time, there's going to be a lot of opportunity for clashes, collisions, and corruption. So that's why we have to latch the data page for the time when we're making that physical change to the data. It's a very short-lived, but it is a point where that can build up a fair bit of contention. Data pages are located or read into the buffer cache, and then they're modified. The log cache record is flushed out to the transaction log, so the log cache again is just a very compact way of describing what change was made. So it's the physical changes on the data page, but just those bits that were changed. It's not moving whole pages around. So that's a very fast, and the transaction log is written sequentially. So again, it's a very fast way to stream changes only out to the log cache. The page is still in the buffer cache, the page that we modified. Eventually, those dirty pages, which means the pages that have been modified since they were brought in, so the version of that page on disk is out of sync with what's more updated in memory. The more updated version gets written out to disk. And that's an asynchronous process. So we're really writing that change out twice. The first one to the transaction log so that we can move on and know that the data is persisted, and then in the background we persist it out to the data files, because the data files are the real canonical representation of the data. creating an in-memory database is so much more than just storing the data in memory. The data's always been in memory. Creating an in-memory database is about rethinking how the database engine works in a world where the two-tier slow, fast, persistent, non-persistent storage is no longer a necessity. Traditional RDBMSs, what you just saw in that depiction, use a disk-based mechanism as the primary storage, and memory is a temporary cache. So although you manipulate the data when it's in memory, that memory representation is just a temporary cache, because memory is the amount of memory available to you is far smaller than the total volume of data that you may be dealing with on disk. And it comes from a time when memory was extremely constrained on systems. You'd have a very small amount of very precious memory, and then you'd have some very slow disks, but they could store very large volumes. You just keep adding disks to the array. An in-memory database, in contrast, is an RDBMS that primarily relies on main memory for data storage. So the primary copy of your data is that copy that is in memory. And then it uses disks for an archive. So an archive is just a low priority. It's not kept within the context of transactional updates, mostly used to rehydrate the memory when the database first starts up, because the data has to get into the memory somehow. So think of it as just an archival storage rather than the active storage that is used during transactions like in traditional RDBMSs. So RDBMSs, traditionally, you're doing your active processing in and out of disks using a cache. In-memory databases, you're doing your active processing in memory and just in the background persisting the data out to disks as an archive. I mentioned that with in-memory, it's no longer just this binary world of disks and RAM, where the disks are slow, they're persistent, and very large capacity. And RAM is very fast. It's the fastest storage you can get, but it's volatile, which means when the system reboots, that data is gone. And it's typically small capacity. That's changing over time. As I said, when these database engines were first designed, the amount of RAM was very small relative to the amount of data that you'd be manipulating. That's starting to change. We have systems out there with terabytes of RAM. But we're adding more options into the picture here. So SSDs came along years ago. SSD is basically non-volatile RAM. It's flash memory with an interface that makes it mimic a traditional disk. So it's significantly faster. You're not dealing with spinning rust, the platters that spin around that have iron oxides to hold the magnetic charges. SSDs are more memory chip-like on the inside. So it's faster, it's persistent, typically not going to be the very huge sizes you can get with some spinning media disks. So it's kind of a middle ground. It's faster than disks, slower than RAM. And what's coming into the picture now is PMEM, so persistent memory. So these are memory chips in the form of DIMMs, so the cards that you use for memory in your computers, but it is made to be persistent. And that can be done in a number of different ways. There's some DIMMs, some PMEM DIMMs that have your DRAM on the one side, which is the RAM that we use typically for main memory. On the other side of that board is flash memory, and there's some form of energy storage, so a capacitor or something that's on that same DIMM chip or DIMM board that has just enough power to, when the power is cut off, it copies all the data from the DRAM into the flash memory. So when you reboot, the data is put back, so the effect is that the data on that memory never goes away through hardware shutdown and restart. So it's extremely fast. It's almost as fast as RAM, typically not quite as fast. It is persistent, and it's medium small. There's PMEM that is significantly bigger than the RAM capacity, but because it plugs into the memory bus, there's only so many slots. So that's the ultimate limit there, is how many slots you have for the memory. So the point here is, instead of a binary world where you have disk and RAM, fast and slow, volatile, persistent, large and small, is very clear-cut, this or that, and the architectures were designed around that binary model. But now we're starting to have more of an array, more of a gradient of options here. So you have slow, faster, very fast, fastest, persistent, 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 volatile, large, medium, medium, small, small. So you have a lot of different options here, and it's starting to be very blurred. That line that was so crisp is now very blurred. So we need to step back and ask ourselves if we're really doing the right thing in the way that we have designed the database systems. So if we step back and rethink the database engine in the modern area where you don't have that binary split, what can we do? What does data storage look like? How can we think about data storage differently? How does resiliency change? How do we change the way we make data persistent in a world where maybe the memory is persistent, or at least some part of the memory is persistent? Can we rethink query processing if we don't have to deal with that same structure? What can we do that's really differently? So we're going to look at the journey of InMemory Database. This has been going on in SQL for quite a while, with the first introduction of InMemory Column Store in 2012, and then came along InMemory OLTP, which you may know as Hekaton, in a later release, and more innovations are coming all the time. So it's a progression. But think of it as flipping the script. So what happens, what changes if we assume data is in memory? If we no longer assume that the canonical representation of the data is in disk, what changes? We don't need pages, right? Pages are just an artifact that is used to move data between memory and disk. If the data is in memory already, why do we need pages? Okay, what's the bad part of having pages? It adds complexity into the system, and it's a structure that has to be latched anytime you change it. You may be inserting one row and somebody else may be inserting another row. If they land on the same page, the page has to be latched, which means those updates can't happen at the same time. So you're going to start getting things stacked up. Without that, you get much better concurrency, much less contention for those pages. That's just one example of things that change. There's a whole lot more. It's a new concurrency model because we don't have the same structures that have to be protected, and we can think things through differently. We can create different structures for how we keep the storage, what the data looks like, that gives us more options. Disk I/O is typically done for durability purposes only, rather than as the primary copy of the data. So that gives us a really different way of thinking about it. Is instead of the disk I/O being integral to transactions where the data is manipulated and updated, it always has to incur that disk I/O out to the transaction log at least, and then the pages have to be flushed out to make room for other pages in memory. If the data is all in memory, you lose a lot of that disk I/O, and that changes things. Database engine is no longer focused on minimizing memory usage. So if memory is no longer this precious, precious small commodity, if we have memory to really work with, as I said, there's some huge systems out there with terabytes of memory. What can we do differently? Index structures can change, right? Instead of being this multi-tiered address where you're looking at the file and the page within the file and the slot within the page, you're doing all these lookups at different levels. If the data you're traversing from one row to another, they're both in memory, why not just use a pointer? It makes it way faster. So we have new query processing modes where we can deal with lots and lots of rows in groups rather than row by row by row. So we're going to start by looking at in-memory column store. Again, this was first introduced in SQL 2012 with the non-clustered column store. So this is the non-clustered column store. So we start with data stored as rows. So we're going to start with looking at in-memory column store. The data stored as rows is how we've been looking at things. So each row is its own entity, all grouped together, and it's a number of rows that are stored in a physical page. Each row has, of course, all the columns in it, and that's how things have always been, right? But if we start looking at large and large volumes of data and looking at how we can do this faster, we rethought things a lot. So this came out of the analytics and big data world. They started looking at the volumes of data that they had to process just to do aggregations, averages, whatever. You're moving a lot of data through the system in order to get that answer. And they're trying to figure out, how can I do this faster? And they looked at it, at the problem as, how do I fit a camel through the eye of a needle, right? And their solution was to make the camel smaller. And so that's kind of what they've done with column store. They've flipped the story again, flipped the page, where instead of the data physically being organized row by row by row, it's now organized column by column by column. We still maintain ordering. So the 10th record in column 1 is still the 10th record in column 2, but they're in physically separate containers. So why does that matter? Well, we compress this data, and each column is going to have the same data type, of course, and it's going to be in the same data domain, which means the values are going to be in some way similar. If you have foreign keys, there's going to be a lot of repetition, so it's going to compress really, really well. So you can get an enormous amount of compression across a bunch of rows of one column, much more so than you could across a bunch of columns in one row. So what we do is we physically store, we have physically separate containers, column by column by column. The other advantage here is that when we're processing a query, the entire table may have 100 columns, but we only need to look at the columns that participate in the query. So if columns C1, C3, and C5 take part in the query, we don't really need to touch C2 or C4 at all. If they're in separate containers, we can never read them into memory. We can just leave them on disk and not think about bringing them into memory. So the more data fits in memory, both because it's compressed really well and because we don't have to move as much data into memory at all. Also, you see it's subdivided vertically, and those are what we call row groups. So we stack a number of rows, about 1 million rows, give or take, in a row group. And each row group has metadata that says, okay, for each column, what's the min and max values, so we can potentially eliminate whole row groups from consideration in a query. So this is an example to make it a little bit more concrete. We have a table here, order date key, product key, store key, region key, quantity, and then sales amount. Okay, that's fairly familiar. We break them into row groups of about 1 million rows, give or take. It's not going to be exact, but it's about 1 million rows. And so that's a unit. We then partition them vertically, so we create segments, and a segment is one column for one row group. So a row group's worth of that one column. So order date key, 1 million rows worth, and then there's a separate segment which is the next 1 million rows of order date key. And each row group is its own entity and has its own metadata. So now we can compress each segment. And again, they're going to compress really well because it's all the same data domain, data type. We do some reordering to enhance compression. We still maintain the ability to reconstruct all the columns in an individual row if we need to. So now look at a query. So select product key and the sum of the sales amount from sales table where the date order key is greater than this date. Okay? So the first thing we note is that store key, region key, and quantity don't take part in this query anywhere. So we don't need to look at those columns and those containers at all. So we never even have to read them from the disk storage. We just cut the amount of data that we're dealing with roughly in half. That's a huge gain. Now we look at the order date key, and I told you that each row group has metadata for each column saying what's the min and max value in this segment. So given that, we can do segment elimination, saying that there's no entry in this segment that has an order date key that's less than 2010-1108. So we eliminate this whole segment. Now we've brought it down even farther, another half, so we're at 3 segments instead of the original 12. So this is just a small example. Between that and the compression, you get like 90 to 95% compression, less data that you have to deal with. So again, we have 1,000,000 rows per row group. Each segment, which is a column in each row, gets encoded and compressed. The compressed column segments then are much smaller. They're dealt with physically. Sys.column store segments will let you look at the metadata for each segment, each column within a row group. It has the min, max, size, etc. And that's how we do that segment and column elimination. Moving on to in-memory OLTP, what has been called Hekaton. I pulled up this slide. This is one from when we were first working on the original project for Hekaton, and that's why the dates are somewhat stale. But the trends, I think, still apply. The idea here was we looked at these trends in processors, and this came from Intel and a few other sources. And we're looking at the Moore's law is still holding, but it's coming in the form of more parallelism. So you're getting more and more cores and logical cores per die, rather than each die being significantly faster. The clock rate has somewhat stalled, and that has to do with the physics of the length of the conductors in there. You get them too short, you start broadcasting data rather than working on it within the CPU. It just radiates the energy out and becomes a heatsink. So that stalled, power's stalled. The perf per clock cycle within a core has also not increased as much as it used to be. At the same time, the cost per gigabyte of PC class memory has gone down significantly, and the availability of larger and larger, to configure larger and larger amounts of memory in a single system has significantly increased. So you can get more and more memory in a system without completely breaking the bank. You put those two things together and you realize that you're going to get faster and faster processing by being more and more parallel, and having more memory allows you to have more data in the working set, which facilitates more parallelism. And that's kind of where Hekaton, that's part of what Hekaton came out of. The name Hekaton, one of the key engineers in the group happens to be Greek, and Hekaton relates to the factor of 100. And so the idea was we'll make this 100 times faster. And that was where that name and that aspiration came from. So the architectural pillars and the customer benefits and drivers in industry. So high performance data operations is the customer benefit. The architectural pillar is its main memory optimized. So if we optimize for in-memory data, indexes, hash and range exist only in memory. The data is stream-based storage for durability. So the durability is just a stream of data. It's not optimized for manipulation as the pages in a traditional file group are. So a memory optimized data, the data in memory has indexes that are hash and range. The indexes exist only in memory. They're not persisted on disk. As you read the data in when the database is being started up, we rebuild those indexes on the fly. And the indexes are in the form of memory pointers, so they really can't be persisted on disk. And the technical driver for that is steadily declining memory prices and also NVRAM. So we can do this, rationally think about putting an entire databases set in memory. The next thing to enable efficient business logic processing, if all the data is in memory, that means we can compile the T-SQL into machine code. That's not really feasible in the case where you've got pages where you don't know whether the data is going to be on the page or it's going to be interacted through an I/O call out to I/O to pull pages into buffer pool and flush other pages out to make room. If you know the data is in memory, you know exactly where it is, you can just follow a pointer to it. And that way you can take whole procs, stored procs, and compile them into machine code using C generate. So we translate this T-SQL into C and use the VC compiler to compile it into C code. And we build a DLL and load it into the engine at runtime dynamically. And so a procedure call is no longer a bunch of context switches going back and forth and pulling things in from memory and interpreting the T-SQL. It's instead just a function call in engine context. There's no context switch at all. And the hardware trend that drove this was a stalling CPU clock rate. So we want to get the most out of every CPU cycle that we possibly can. The business benefit, of course, is efficient business logic processing. Frictionless scale-up is facilitated by high concurrency. Within Hackathon, we use multi-version optimistic concurrency control with full ACID support. So we have the same ACID guarantees, but by using a multi-version concurrency control, much like snapshot isolation, we can get much higher concurrency here. And because we don't have pages to get in the way with latching page latches and all that, there's just much less chances for collisions. In fact, the core Hackathon engine is completely lock and latch free. There are no locks or latches in Hackathon. So you're not going to be waiting on lock manager, latches, spin locks, any of that. So that makes massively more parallel processing much more possible and efficient. And then to have a hybrid engine integrated experience, it's tightly integrated into SQL Server. So this isn't this new exotic engine off on the side that maybe you can use or maybe you can't. It's part of SQL Server. So the same manageability, administration, development experience, integrated experience, queries and transactions, all that gets you that reusability. The biggest change you'll have to adapt to is the concurrency control, the optimistic concurrency control. It has some logic impacts. So what does it look like? So in memory, the data has a header, which is constructed when it's brought into memory. You have the begin timestamp, which is the timestamp when this version of this row was created. And if the this row version is superseded by another one, there will be an end timestamp there, or if the row was deleted entirely, you have an end timestamp. So we know the range of times when this version of the row was valid. You have a statement ID, and a count of index links. So the index links are in memory. So these are just pointers, right? This is all in memory, so it's a memory pointer. So it's 8 bytes times the number of indexes there. So that's all packed into the row header, and then the data here is the payload. So that's what a row looks like in InMemory OLTP. The timestamps are used for optimistic concurrency. That's how we get the lock-free, latch-free. So we know when each version of each row was valid. We know that if you are going to modify a row that has been modified since your start of your transaction, then you can't do that logically without creating problems, so you have to back out. Indexes are physical pointers rather than structures. So we've looked at a couple different forms of in-memory processing, column stores and in-memory OLTP processing. How are we taking advantage of that today? So those are things were invented in prior releases. They've been refined certainly going forward, but they're not brand new technologies. What is new? What are we bringing forth in SQL 2019? We looked at some of the TempDB contention that we have. TempDB is created from scratch every time that we start the system, and so the durability of TempDB really doesn't matter that much because it'll be recreated after the restart anyway. So the type of contentions that we see are object allocation contention, contention for metadata pages, used to manage space, allocation of the data file. So it's space management data. And to find that, you're going to look for page latch weights on the PFS and GAM pages, which are special pages that track space usage within the data files. Metadata contention, so contention for pages that belong to system objects used to track table metadata. So look for page latch weights on pages that belong to system objects. And temp table cache contention. So there's contention for memory objects associated with the temp table cache. So there you're looking for CMEM thread weights or SOS cache store spin locks. Both can be due to other causes. So those are the things that in TempDB will slow you down. If TempDB is causing you headaches, this is kind of the root of where a lot of those are coming from. And to give you an idea of some of the things that cause this and some of the things that we've done to make things better, there's a lot of contention on TempDB is increased exponentially. It becomes a major bottleneck. So one of the scenarios here is that memory pressure triggers a cache clock and sweep to move items to the deleted list. So you fetch one, background process cleans up delete items from the deleted list and removes the corresponding metadata. If the background thread falls behind this background process, and keeping the list at a reasonable number, all create threads get co-opted to become helper threads in keeping this under control. And you have all these threads here that we're doing deletion and cleanup, and across all the different NUMA nodes here, doing deletions and conflicting here, and everything just comes to a screeching halt. What we do instead now, instead of having all create threads being co-opted, we now only one thread per NUMA node, so that's a range of memory container for the NUMA node. So only one thread per NUMA node is used as a helper to delete things, and you have far less contention on these sysobject values. So I'm going to do a demo here of TempDB memory optimized metadata. One of the other facets you should know about InMemory OLTP is that tables can be either durable or non-durable. So if you have a non-durable table, all of the same guarantees and processing takes place, but nothing is put out to disk. And that's what we're using in TempDB, because there's no reason to persist it. It's TempDB. So let's hecantonize TempDB. So I'm using Azure Data Studio here for this, and just a few words about Azure Data Studio. It's a really useful tool. It doesn't completely take the place of Management Studio, but what it's just excels at is the fact, what sets it apart is that it has the capacity to host Jupyter notebooks. And notebooks have this interesting characteristic of having, a notebook can have text cells or code cells. And a code cell can be a number of different processors. So the kernel can be SQL in our case because we're doing SQL coding, but you can have Scala, R, Spark, Python, PowerShell, and there's more coming. In our case, we're using it for T-SQL. Attached to a given instance, but it makes it really nice to have self-documenting procedures. So you'll find a lot of sample code and demos and examples on GitHub, SQL Server samples in GitHub. That's where I pulled this from. And it just walks you through what we're talking about, step by step, what you're doing. So this is how you configure things. You do the database restore, you make a special procedure in AdventureWorks, and then it shows you how to run the demo, and it's interspersed. The code blocks in here are actually live, so you can execute this, and I'll show you that in just a second. So what we're doing here is we're going to use OStress, which is a multi-threaded stress tool, simulate stress. We're giving a query to build the birthday list. We're doing 20 threads, 120 repetitions. So this is getting a lot of contention, which is creating, deleting objects, and that's going to hit TempDB pretty bad. So we're going to start this and then go over here and run this query, which should look for page latches in TempDB. So we're running it, see all these page latches on sys schema objects, execute, create table, execute, and now it's done, so you should see them all gone. So that's how you can see that you're getting all these latch contention on TempDB. You probably don't need to run special queries to know that things have slowed down, but this is a way to see it very specifically. There's a server configuration to set memory optimized TempDB metadata on. So we're going to do that now. We're going to turn that on. So now the TempDB metadata is held in memory optimized form. And that's going to take a server restart, which I'm going to do off screen. Restart the server. Do you want to restart? Yes, I do. Stopping the instance, starting the instance. Okay, so now we should be able to find, we can run this query. Server property is TempDB metadata memory optimized. Find that to see, and indeed it is now memory optimized. So now we're going to go back to that same scenario where we have running OStress with all of these, and there's no blocked threads. Just no contention here. And it's done. So if you look, it's significantly faster and there's no contention. So that's how we can show the effect of the hecadonized TempDB. So coming back to our presentation, fast and volatile and slow and durable, 2 tiers. So we've had 2 tiers. That's no longer the case. We've talked about that. NAND is what SSDs are made out of. 3D NAND is faster NAND, which is a whole new universe. Faster NAND is a whole new universe. Storage class memory is a kind of synonymous with PMEM. It's persistent memory is NVDIMN, which is what I talked about, that has the DRAM and persistent memory on the same board with a capacitor to facilitate just moving it back and forth. So we have this classic pyramid. We have DRAM, storage class memory. NVMe is like an SSD, but it plugs into the PCIe bus, so it's much faster than a traditional SSD. Fast SSDs, capacity SSDs, and then hard drives or tape. So you've got this pyramid of storage. So SQL Server and PMEM. So what do we have here? We're doing some rethinking in how we can integrate this. This is work that is being done now and thinking that we're working on. So PMEM can be configured in the OS to be surfaced as if it were just a block device. So it looks like a really fast SSD, for example. SQL Engine sees it as another block device, kernel I/O to your data and log files. So that's the simplest way to leverage it. It doesn't require any code changes. It just looks like a really, really, really fast disk. If you start taking advantage of the fact that this is a memory board, even though it's persistent, in SQL 2016, we took the first baby step along this path. Log records are held in a cache and then flushed out to disk. And traditionally, we haven't allowed the transaction to complete until we have confirmation that that flush has happened and it's persisted in durable storage. But if the log cache itself is kept in one of these PMEMs, if you can take a PMEM and format it, it's called DAX mode, where it can be mapped into a memory space. So it's like a memory mapped file. But the file is persistent. The address range you get is that PMEM. So that memory is persistent, and you can find it again after a reboot. Then the log cache itself is already persistent. We don't have to wait for the I/O out to the disk. So that means we can move the transaction and complete the transaction without ever waiting for the log records to be flushed out. So it makes for higher concurrency and faster throughput. Enlightened I/O is something that we're working on right now, where the SQL engine, if we map the MDF or LDF files as PMEM, then we can do kernel I/O directly to those files from the SQL engine. So we can basically sidestep the whole OS stack, OS I/O stack. A hybrid buffer pool is also in SQL Server, where we map the MDF file into a range of memory within the buffer pool. So it looks like we're dealing with the buffer pool, but we're dealing with the storage, so there's no need to flush pages back out. Hybrid buffer pool, you place data files directly on PMEM with DAX mode, so that's byte addressable storage. You don't need to copy pages to DRAM as in the traditional buffer pool, because it's already there. That's where it's permanently stored, is in the PMEM. It eliminates I/O, right? So instead of pulling it from disk, doing I/O to get it into memory, it's permanently stored in memory. The memory is just persistent. So your buffer pool now is a big range of persistent memory. Considerations: it applies to clean pages only. It's not compatible with buffer pool extensions because the whole buffer pool is now in memory. It's not compatible with pages using torn page detection or TDE. At this point, Optane encrypts the data at the device level, so database encryption. You can't shrink DB files when this feature is enabled. We just don't have the mechanisms in place yet to be able to shrink the data files when they're in non-volatile memory. How do you get it? Put your database file on a PMEM device with DAX equals true. alter server configuration, set memory optimized, hybrid buffer pool equals on, restart SQL Server instance, and then alter database, set memory optimized equals on. That gets you this behavior. So it's fairly straightforward, not a lot of changes on your part, it just goes faster. That's kind of this mantra we like. It's like, you don't have to change a lot of things, it just goes faster. So what does the future hold? Our approach to persistent memory, PMM enables both lower storage latency and increased memory capacity. PMM comes in much larger denominations. It is persistent storage, so we have much lower latency. It's just memory access on the memory bus, and your memory gets increased by that amount as well. Real-world performance gains with minimal trade-offs. You avoid unnecessary complexity, we balance performance gains with cost, and you make it manageable. It should just work. You don't have to spend a lot of extra time managing the system because it just works. So this is where we're headed. This is the next step along the journey. Some pointers to resources. So want to download SQL Server 2019 and try it out. You have the What's New, SQL 29 What's New documentation. Great data-related demos, data demos, IQP, Intelligent Query Processing, SQL 2019 notebooks. I've mentioned that a lot of the samples like the ones that I showed you are published. That's where you can find them. There's a new book put out by a couple members of my group, Pedro and Pam, T-SQL Querying. Highly recommend it. And the one shortcut to rule them all, aka .ms SQL shortcuts. From that one, you can find all the other shortcuts for SQL data. And you can find free training, SQL workshops. So this is all the materials we use for in-person workshops, just without Bob Ward there. So thanks for your time.